Oh yeah. I don't know. I should have started with a blank one. There you go. All right. Now, dig this, guys, in 4, or not 4 dot anything, 6.4. Here's kind of what we're faced with at the beginning of it all. 6.4, we're getting into logarithmic equations and inequalities. We've seen some of those already. We'll put log equations for now. That'll be good. It's not good to make your Q look just like your G looked, because they're supposed to be different letters. So maybe we'll doctor up the G to look cooler. I don't know. Almost feels like my Q is backwards when they look that similar, but it looks, I guess we're fine. Anyway, so when we're talking log equations, sort of like the heart of it all would be things that we've seen in the recent past, where it'd be, I guess, something like this. Say we had something like log base 2 of x equals -3 or something. And this is an equation to be solved, but it has the x in the middle of the logarithm. It's in the, it's being logged. And so that makes us it puts us in a funny position, because now instead of it being like logarithms are a benefit to us, we're back in square one where we started out, where it was like logs are kind of a mystery. And I can't really use this in logarithmic form. I got to probably put in an exponential form to solve this out. Although there are other funny ways to do log things, but this is what comes to mind for me. So if I saw this, I would probably go, let's find an equivalent form in exponential notation. And then we'll be like, well, let's see here. This would be, if I put in an exponent form, that's 2 to the, what's the power going to be? You guys remember how this goes? This would be 2 to the, guys.
-3.
All right. 2 to the -3 power equals x. Loving it. And then what's good about that is then we're like, oh, we've seen these before. This is nice. The x is actually by itself by the time you get there, so that you're really just done. There's no solving to do. You can simplify the answer, write it in maybe a different form, but basically x just equals whatever 2 to the -3 is. You might even be able to write it in that way in the answer box. Otherwise, remember, a negative power is 1 over 2 to the 3. Or this is 1 over 2 times 2 times 2 is 8, so you could say it's 1/8, that would be fine. Any of those should be fine. I'm not sure which way my open math wants it. Anyway, we've encountered equations like this before. And so I wanted to now, before we have you guys practice them, kick it up a notch and show you some other variations. So if I had something like this, here, check this out. What if I had log base 2 of x to the 3 equals 5, Now it's like same kind of thing. It's just that on the inside of the logarithm, it's not just x, it's like x to the 3. So that's pretty cool, I guess. But then help me to translate this, guys, into exponent form. If we put that in exponent form, because we still got the x inside of the logarithm, so that's going to be hard to deal with. So maybe we'll try exponential equation here instead. Okay, so this would be base number is still, what's the base number still? Guys.
2.
Yes. I knew you knew. And so base number is still 2 up to the 5 power equals that x to the 3. And this is good. It's just that we're in a memory jog here where we're like, well, 2 to the 5th, I could figure that out. That's whatever. But I have to remember how to get the x by itself. How do I undo a 3 power? Anybody remember how to undo a 3 power?
Square root it?
Yeah, 3 root
And isn't that divided?
So
isn't that 3 divided by 2?
It's like the 3, except that if we were to say x times 3, then we divide the 3. If we
So it's x to the 1/3 power, or 1/2 power.
Oh, I'm with you. Yes, it is. It's like a divide 3 power, if you will. Yeah. And so x to the 1/3 power, or else known as a 3 root, but yeah, the 1/3 power thing totally works. And then now we're just cooking it. And so let's see here. Now we got x on the right hand side just sitting there by itself equals this whole mess. And then sort of like Jude was maybe getting at, there's other ways to write this. So if you feel like it, you could probably get away with writing it like this and just call it 2 to the 5th 3 root of that. Or else feel free to write it in other forms. If it doesn't take your answer like that, there's different ways. You could certainly write this as 2 to the 5/3 power. Or else if you like, you could say 2 to the 5th is 32 and just say that it's the 3rd root of 32. That would be fine. That's also fine. I'll even put that there because 2 to the 5 is 32. So you could say that's a 3 root of 32. That would be fine. Probably I would lean towards one of these first two, but I imagine it would take the last one as well. Anyway, as long as you got x by itself, we're cooking. Okay. Now, we pickled pineapples. Check this out. What if we said this then? Cynthia, I want you to check on my swimming pool every once in a while. Just peek out the window and let me know if it is.
Yeah, definitely. I got you.
Okay. Let me know if it's leaking or not. Let's see here.
What?
Yes. Okay. So here, there's other weird variations. What's that? Everything all right? Feel like something's going on. Okay. So here's a situation you run into in your homework that I figured like it was dizzying enough that it's worth talking through. Here, actually, let's do that on a different slide. Here, check this out. What if we had log base 3 of, dig this, log base 3 of x equals, whatever, 4. Not that they both have to be log base 3, but it's, these weird stacked logarithm things going on. And the fact that my first L looks like a parentheses doesn't help. So maybe let's straighten that out. Okay, that's looking good. Okay, we're still not leaking. All right. Dig this. I feel like we're getting some background noise. Just make sure that you have remembered to mute yourself when you're not talking, guys. Now dig this. If we're to go in exponential form, this is super weird because even if we do, it's like, well, okay, so let's see here. The base number is 3. So that'll still be true in exponential form. So an equivalent form here would be, I'll start with base number 3 up to the 4 power still equals whatever the heck is left. But that's all of this. It's the innards of the log, which is a whole other logarithm. Log base 3 of x. That's the innards of the first logarithm. And now you're like, well, it sort of worked. It's better than it was before, but it's still a logarithmic equation. It's still logarithm form. And so now maybe we'll just find an equivalent form of that and put that into more of an exponential notation. Let's see here now. Base number is 3 still because of this little 3. So we got base number 3 there. 3 to the this mess, 3 to the 4. What? Because of an order of operations issue, I might suggest that we figure out what 3 to the 4 is. Anybody got 3 to the 4 power?
81.
It is. So we'll just call that 81. So we're going to say in exponential form, this is 3 to the 81 power equals x. There you go. 3 to the 81 equals the x inside the log. And now it's like, finally, we got the x by itself. There's no way I'm going to figure out what 3 to the 81 power is. It's like billion. So we're just going to leave it at this. It's 3x equals 3 to the 81 power, you know? And then I have one other variation I wanted to show you guys. It's sort of along the same theme here before I pause the recording and have you guys try a little bit. Check this out also here. What I also see here is this kind of a thing showing up. If I had log base whatever, you know, say 3. We just did 3. Ew. Log base 5 of 4x minus 2, 1, 2, 1. 4x minus 1 equals, say, 2. Now, it's like, well, okay, this is continuing in the theme of stuff inside of the logarithm is just a mess, you know, instead of just being an x. But it won't be that big a deal for us because I feel like we can handle this. What's the base number still going to be if I put this in exponent form? What's the base number still going to be here, guys?
Five.
Oh, yeah, it sure is. So we got 5 there. 5 up to the 2 power equals the 4x minus 1. Looking good. We're feeling it. And now it's like solvable. We can figure out 5 to the 2. That's just a number. That's 25 equals 4x minus 1. And then it's like solving time. We can do this. Guys, how do I get rid of the minus 1?
Add it.
Yes. Plus the 1. Look at this. It even divides well. I thought we would get a fraction. Oh, yeah, never mind. We're going to get a fraction. I should have done 4x plus 1. Oh, well. Anyway, dividing the 4. Then we got ourselves x equals just 26 over 4. Maybe reduce it if you get the chance. That's 13 over 2. I love it. I am going to have you guys practice a couple of these. Yeah, let's do that. I'll take your temperature later when it's not recording so you don't have to feel like you have to be on the recording. So check this out. Right now, let's go ahead and get a few variations for you guys to try out. First off, let's try log base 4 of x to the 3 equals 2. Also try log base 3 of log base 2 of x equals 1,000,000, or what shall it be? Let's do 5. Oh yeah. And then something seems funny about that. I don't know. We'll see. Hopefully that doesn't go too weird. And then also log base, let's do 4 of 7x minus 6 equals 3. All right. See what you can do with that. Take your time. I'm going to pause the record. All right. Help me through here, guys. Let's see. I'll pick a different color, I guess. Now we got log base 4 of x to the 3 equals 2. Talk to me, guys. We have, this is a log base 4. So base number is still going to be what, guys?
4.
Yes. So we got base number 4 up to the 2 power equals x3. And then it's like, whoa, how do I get rid of the 3 power?
Cube root.
Yes, I love it. And so we're all, it's 3 root time, but boom. Oh, whoops. I never did take y'all's temperature. See how you've been doing with this stuff. Maybe I should have. That's bad. One-way communication, no good. Okay, so now we have, essentially it's just that. It's a 3rd root of 4 to the 2. You could probably get away with writing it that way. Or else you could say this is 4 to the 2/3 power, that's fine. Or if you like, you can figure out what 4 to the 2 is, that's 16, and just call it the 3 root of 16. That would be fine as well, and that actually reduces out a little bit if you take pairs out of there, or whatever we do. Anyways, there's different ways of writing that. You can even go decimal form on it if you get a calculator out and just say 4 up to the 2 divide 3 power, and then it'll give you 1 point la la la, you know, something weird. And so that works too. Okay, let's see here. I think this one next. Yes. Okay, so we were translating this one. It was like log base 3 to the whatever power. So that's base number is 3 to the 5 equals log 2 of x. Looking good. 3 to the 5 equals the whatever. And then we had to double translate it because right now it was double encrypted, you know. So an equivalent form of that, we had log base 2, so base number is 2 to the whatever the heck 3 to the 5th was. And so again, because of a funny order of operations confusion, I recommend that you do go ahead and figure out what 3 to the 5 is. Anybody got 3 to the 5?
$243.
Yeah, it sure is. 243. Very good. So then we got 243. Okay, looking good. Let me make sure I didn't mess anything up. It's 2 to that power. So 2 to the 343 power. 243 power equals x. Looking good. Okay. Equals x. Hopefully I'm still on your whiteboard. I know it cuts out down at the bottom. Now we got x equals just that though. It's just x equals 2 to the 243 power. Looking good. All right. From there, now we got all this mess. And so we would say, I guess 4 is still the base number to the 3 power equals 7x minus 6. And then just a matter of trying to figure it from there. 4 to the 3 we could probably figure out. And then 7x minus 6, we can get to x by itself, you know. Anybody got 4 to the 3?
64.
Yeah, it sure is. That's 64. And then wham, wham, you know, plus the 6 and all that stuff. Yeah, 7x equals, what is that? 64 plus 6 is like 70. Oh my goodness, look at it. It's beautiful. Because I'm about to circle it. 70 divided by 7, it's just 10. We actually got a whole number for once. I love it. I was just thinking about this the other day. And I think that it's a super complicated problem to try and figure out. I imagine it's been looked into before, but because it's just sort of a number theoretic thing, not this cool spiral that I'm drawing, that's cool too, but I was thinking about like if you took any two numbers in general, say integers, and divided them, you know, big one divides small one, say, or just any two, what's the probability that they would divide to become a whole number, you know? What's the probability that a rational, well, I guess well, anyway, as I'm thinking that through, there's other ways to look at the problem. Anyway, who cares? So we have ourselves something that actually divided to be a whole number now, and we're looking good. Do you guys know, believe it or not, this funny spiral thing? Well, who cares about that too? We'll talk about something else. Okay, dig this. Other variations that we run into here, guys, though, that I'm thinking of is like, dig this. Here, check this out. What if we had this log base? We'll just do common log. We'll say common log of, and then it's like x or something, plus common log of x plus, say, 5 equals 1 or something. We're looking there. And then, guys, before I get too far along, tell me about this. If we have a log and the base number is not specified, what the heck number is the base number? What do you guys remember about that?
10.
Yeah, it's a 10 base. Very good. Yes, 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 it's a base 10. So just remember when you see that, because they're throwing that around the homework, there's some common logs around. Remember, that's a 10 if you ever need it. And so we're in a situation here, guys. We're supposed to solve for x, and it's kind of like the backwards of the situation we had before. You know, we've talked about when the single logarithm is too complicated because the insides of it are too much to figure out. We can expand them into multiple logarithms. But this seems to be a case where at least it's x and an x thing. Maybe it's too much to deal with this as two separate logarithms. Like, how do you get x by itself when it's in two separate logs? Like, each one of them is still trapped in a logarithm. And so it might be easy to break them out of the log if we put them all together in a single logarithm first. And so what you guys might remember is when we were in the warm-up, you guys might remember if we had the whole log with the x, y, z and all that, you know, sitting in there. And we were like, let's break that apart into separate logs. And we were like, oh, if they're timesing and I want to pull them apart, then times is like plus when you pull them apart. In this situation, we have two different logarithms, and we're going to try and glue them back together so that we can deal with the x's all at once. And so, guys, tell me if I'm going to glue these back together as a single logarithm, and we're like just log of something, and I'm like trying to glue them back together. Tell me this, if I'm gluing them back together, then plus is like what?
Timesing.
Yeah, matter of fact, if we're going to glue them back together, then it's the other way around. Then plus will be like times. So if we glue them, then this and this will be timesing. We have log of x times with x plus 5 equals 1. And then it's like, well, that sort of helped. But at least now it's all one logarithm, and we can find maybe an exponenty way to say that. And so remember, this is log base 10, like you guys were telling me. That's a log base 10 there. And now we'll be like, well, okay, in exponent form, that's 10 to the 1 equals x times x plus 5. Whoa. X times x plus 5. Looking good. And then it's like, I don't know, we'll just see what we can do. X times x plus 5 is doable. X squared plus 5x, that seems all right. 10 to the 1 is easy, that's just 10. But now we're in a situation that we used to see ourselves in a lot, where we got an x squared and an x in the problem. This is back to quadratics that we ain't seen for a few weeks. How in the world should I handle this? What should I do? What would you guys do? At least to get started on this thing. Ideas? What ideas do you have on getting started?
Can you like equal it to 0?
Yes, I love it. Precious comes in with an amazing idea. We're gonna say maybe we could do it that way. Yeah, there's other ways to do this, but that's not a bad idea. She's suggesting maybe we could be like, well, why don't, since it's got a quadratic mess going on, maybe we could get that thing equal to 0. We'll take the 10 maybe and minus the 10 over to, you know, the other side. And then we just got 0 equals, and then it's x squared plus 5x, then take away 10. And then it's like, yes, maybe this is familiar territory, and we're just desperately hoping that this will factor. We're desperately hoping this will factor. I guess that's another way to think of that same weird problem about the dividing. But help me out. I need numbers, 2 numbers that times to 10 minus that add up to 5. What numbers are going to work for this? Anything times to 10 that adds up to 5? You guys got anything? That's what I came up with too. I got nothing. Maybe we'll just go with that then. It looks like A's saying, I don't think it's going to factor. So what do you guys remember about this? Won't factor. How do I handle it when it don't factor like that? What do you guys do? What do you remember? Where else could I go?
Quadratic?
Sure. Matter of fact, yeah, that leaves us with only a few options. We could maybe do complete the square or something, or else just, yeah, shoot it into the quadratic formula. And so then let's go ahead and go that direction, I guess. Here, I think we'll need a little room. If we take it from where we were like x squared plus 5x minus 10 equals 0. And then it's like ABC gum time. And so then let's see here, x squared is like a 1, or I mean, you know, and then 5 for the b, and then c is minus 10, and then you're just kind of going to town. Let's see. If we did, the b term is 5, so let's see here. Don't let me mess up. That's negative b plus or minus b squared is 5 squared minus 4. A and c is 4 times 1 times minus 10. All over 2a is 2 times 1. Now we have negative 5. Let's see here. Okay, don't let me mess this up. Tell me, guys, how do I do this? If it's a minus times another minus, what's that going to be like?
Positive?
Yeah, it is. It's like a positive or a plus. That looks good. Checking on the pool. Okay. And then we got 5 squared here is 25. And then, like you say, it's a positive. Minus times minus is just like a plus, and that's a 40. So this is 25 plus 40, whatever the heck that is. And then there's a 2 sitting there. Now let's see here. We have negative 5 plus or minus. Anybody, what is that? 40 plus 25, 65. Radical 65 over 2. And then we're just, now we're stuck at kind of trying to figure out the answers. Now I have a bit of advice for you guys on what we're dealing with here. You guys know with quadratics, or anytime you have a square root when you're solving these things, use a plus and a minus version of it. There's negative 5 plus the square root of 65 over 2. And then there's negative 5 minus the radical 65 over 2. And so we got to figure them both out. Or you could just maybe shove them in the answer boxes like that even. But I have a bit of advice for you about these things. There's an issue that we have to talk about. We should talk about that in just a minute here. But I'm going to tell you that probably, typically speaking, because of something we're about to talk about, normally the minus one gets thrown out because there's issues with minuses and logs, or logs of negatives. So you'll notice that a lot of the time these ones, they'll be looking for one answer and they won't take both of them from you a lot of the time. And there's reasons for that that we'll talk about. But essentially, we're probably looking at just the plus version. Now, let's see here. Anybody got a calculator around? Do you guys mind, anybody that's got their phone or a calculator or something on, do you mind helping me out? Run some numbers here real quick. I want to get, what's the square root of 65? It should be like 8 point something. Figure that out real quick, guys. Let's do that together. Square root of 65. I just messed it up. 65. I'm getting 8 point like bunch of stuff. You guys getting the same kind of thing?
8.06225705.
Yeah, that looks good. Okay, that's about what I'm getting. So maybe we'll start there. Okay, so if we got that, this is negative 5 plus, and then we'll say this is a wiggle equal to 8 point. Yeah, if we go 4 places out, 06, 2, 2, and then like you say, it's like 5 and all this stuff, whatever. Keep that on your calculator uncleared. I'm writing it out with the dots there, but just keep it uncleared and it'll be like 8 point, all that mess. I'm sure you can see it real well. Here, we'll get, what if I hand a shaky hand? That would help, right? Anyway, and then it's all of that over 2. And so if you don't mind, guys, what we'll do is we'll take the positive square root, which we already have, which is The positive square root of the positive square root of 65 is 8 point whatever, and then plus a negative 5, because you see how it's like got negative 5 plus that 8 point whatever. So we'll do that 8 point whatever it is on your calculator plus a negative 5, or you can just put minus 5 if you want. That take away 5. So I have radical 65 take away 5, and then that'll be 3 point something, I guess. And by the time you get there, then you're just going to divide it by 2 like we do. We'll just divide it all by 2. And so then I'm getting 3 point all this mess, and then I'll hit answer divide by 2, and I'm getting, it's looking like wiggle equal to about 1.5311. You guys getting about the same thing?
Yeah. Yes.
Cool. If you're getting that, then we're cooking. We're square at that point. So only advice I have about that is if you can avoid clearing your calculator until you're done, so it has that whole big old string, so you don't have to round it off until the very end, you're probably better off, just like we did. Anyway, that's kind of what they'll be looking for. Sometimes you can get away with just putting it in radical form as well. If you can type the negative 5 plus radical 65 all over 2, that also tends to work. But I like to get a decimal approximation so we can get our minds around the fact that this is about 1.5 positive. And here's another variation before I have you guys practice any. That one I know tends to be tough. And here's something that's maybe not quite as tough, but it's in the same family of problems. If we had this and it was like log, here, let's see. Log of, it's a common log again. Or we'll just do log base 2, I don't know, of x plus 5 minus log of x minus 4 equals 7. Tell me, guys, about this. These are 2 logarithms. We're going to try and squash them into a single logarithm so we can free the x's together. But tell me, if it's a minus and I squash them back together, minus is like what?
Division.
Yes. Man, yeah, minus is just like divide. So we're going to say it's a minus becomes a divide of the x plus 5 and the x minus 4. It's like a divide. So we have log base 2 of all that mess equals 7. And now we can find an equivalent form. I could be writing in an exponent form and free those x's. And so we have 2 to the 7 power, 2 to the 7 equals x plus 5 over x minus 4. Now 2 to the 7 is a number we could figure out. So that'll be okay, I guess. You know, it's not as big a deal as the last one because I don't think that we'll have to do any quadratic stuff on this. 2 to the 7 is, oh shoot, okay, 2 to the 5 is 32. So we're looking at 128, I believe. Is that right? Let me just, we're going to rewrite that. Is 128 correct? Is this thing on? Is 2 to the 7th 128?
Yes.
Wondering, yeah, okay.
Uh-huh.
We have one witness confirming it now. Okay, we'll go with it. Okay, x plus 5 over x take away 4. Thank you, by the way. And then from there, I need ideas from you guys. What idea do you have? I have this fraction here. I would like to not have a fraction there. How can I get rid of that x minus 4 so it's not like on the bottom sitting there? Dividing. How can I undivide it? Yeah, I love it. We'll be times in it. That's good. X minus 4, x minus 4. We could just times it out to the other side. So then it's like, well, x plus 5 is what it is. It's sitting there by itself. But over here we have 128 timesing with the x minus 4. And then we could figure out that, I guess. 128 times x is no fun. But then 128 times 4. Somebody got that for me? That's gonna take me a second. I feel like that's over 500. Is it like 502 or 512 or something?
512.
512? Okay. Oh yeah, because it should be a power of 2 as well. So 512. That's pretty cool, I guess. And then it's like we got to get the x's by itself, but there's two different ones. So like maybe I'll move one of them. This is a 1x. You guys okay if maybe I just minus the 1x over here? Minus 1x. And then what is that? 127x minus 512 equals 5. And then we'll just, at least now we can like solve it, you know. How do I get rid of that minus 512, guys?
Had it?
Yes. We'll plus it over there. Plus 512 like we do. And then let's see here, 127x equals, what is that, 517, I guess? Oh gosh, it looks terrible. 517. Dividing it up, we're as good as it gets. Shucky ducky. We got ourselves 517 over 127. I don't think it reduces. I sure hope it doesn't. And there you go. Good chow. So this one ends up being not as big a deal, because sometimes when you got the rational ones, you know, maybe you don't end up having to do an x times another x. It just depends on what you're dealing with. So these ones are not as bad, but I definitely wanted to kind of give you a chance to see them. So let's, I'm gonna have you guys practice one or two like this real quick. To take your temperature in a second here too, but again, I'll let you do it off of recording. Let's see what you can do with this. Let's do common log of x plus 8 minus common log of x minus 3 equals 2. Remember, it's a common logarithm. What's the base number if I don't say?
10.
Yeah, it's a 10, guys. Very good. Cool. Let me pause this recording here and then we'll give you a chance and I'll see how y'all are doing finally. I don't actually know. We got a problem. Oh, no, we're okay. All right. Talk to me, guys. I got this mess going on. Where's it at? This is a minus. So if we're going to put these things down into a single log, minus is like what again? I was scratching my head and I didn't hear what you guys said. Did somebody say something? Oh, yes, divide. And so then we have x plus 8. What if I scratched my head so loud that you guys heard it? What would you do?
I think I did hear it.
That's funny. Okay. My kids have this joke saying that I'm a Terminator, and I'm not really sure why. I don't remember why. But I'm sure they would appreciate the loud head scratch. They're like, what, has he got a metal skull in there? Okay. I don't actually remember where I learned that or where they got the idea from. So dig this, guys. We got this. It's a common log, though. So you guys are like, well, I guess it's a 10. So if I'm putting this in exponential form, maybe it's like, what do we got? This would be 10 to the 2 equals all the other stuff. And now it's good because we could do 10 to the 2. That's 100 equals x plus 8 over x minus 3. And then tell me, guys, how do I get that x minus 3 out of there? Tell me, guys.
Multiply it?
Yeah. We'll times it. We got x minus 3 timesing. I love it. Boom. And then x plus 8 seems to be left over on the right hand side. And then on the left, it's just like 100 timesing with the x minus 3. So we'll just distribute that 100 times x, and then 100 times 3. 100 is nice in that way. And then it solves very similarly to the last one. That's a 1x, so we can minus it out. And we'll just get like 99x, I guess, minus 300 equals 8. And then we're just solving it. Don't let me mess this up. I'm going a little bit fast here because you guys got to do it before I did. What is this, 308, is that right? And then if I divide that up, I'm getting 308 over 99. Are you guys getting that too?
Yes.
Yeah.
All right, cool. All right, so then that's my take there. I'm glad. Okay, so here's the other thing I wanted to bring up, and then we'll get you guys on break here. Recall something. Notice. Recall. Notice. We'll just say notice. Okay. Notice something with me about logarithms. Okay, if we were to say like take 2 to the x equals y, you know, we got y equals 2 to the x, like y is a function of x or something. We can do a little in and out thing. Although I made my chart kind of bendy, but whatever. We could plug in numbers for x, and then that would give me the y values, just like we have done so many times we've done this. And so, like if I plugged in a 5 for x, then we'd have y is just going to be 2 to the 5 would be the y, you know, and then that's whatever, 32, I guess. And so let's see, then we'd say, oh, it's 32. No big deal. And then, you know, you can do weird things and you'd be like, well, what if you plugged in 0, you know? But that actually doesn't become a problem. 2 to the 0 and then would be the y value, but 2 to the 0 is just 1 because of a discussion we had last week, you know? So that's not a big deal. So it's like, okay, we're trying to mess things up and it seems like you could, but then it ends up just keep working out. So you're like, okay, well, what if I plugged in a minus, you know? What if I plugged in a negative for x? And I feel like that's not as big a deal either. 2 to the minus 5. It's weird, but we can do it. What do you guys remember about 2 to the minus 5? How do I handle that?
Do you turn it into like a fraction?
Yes, that's right. Looks like that beautiful.
Oh, I'm right. Hey.
Very good. Right on the money. And so, indeed, yeah, it's like fractiony. This is 1 over 2 to the 5th. Yeah, right on the money. First shot. And so we got whatever that is. That's 1 over 32, I guess. You know, 2 to the 5th is 32 still. So this is 1 over 32. And I guess like she was getting at, like we can do the fraction thing even when there's negatives. It seems to be the case that here's what I would make from that. Even if you wanted to plug in like huge numbers and we were like negative 1,000, you know, or whatever, like if we plugged in 2 to the negative 1,000, it doesn't really matter. What ends up happening is that it's just 1 over 2 to the 1,000 power. And I mean, I don't know what 2 to the 1,000th is. That's giant. But it's like, it's just 1 over some huge number, you know, 1 out of a billion. So it's a tiny, tiny fraction because it's 1 out of a million or a billion, you know. So whatever. But what I'm noticing about it is this. The x values here, it's like, it doesn't matter what you do. You can get away with anything. So if we were talking about domains in an exponent situation, you could plug in anything you want. There's no restrictions on it. But I do see something happening funny with the output numbers. Notice something with me on the output numbers. It's kind of Fruit Ninja like. What if on the output numbers, notice how it doesn't matter if you plug in a positive or a negative or even 0. Notice how these output numbers never quite go negative. They always stay positive. They don't even quite get down to 0. Like you can plug in the most negative number you want and you never quite get negative. You just keep getting fractions. And so with the outputs, with the y values, it seems like they always just stay positive no matter what. And that's weird to me. You can plug in anything you want on the x's, and the y values, they stay positive. And that's, I mean, that's an interesting thing to notice in itself, but, you know, as powers of 2, but it seems like if we were to go, you know what, this thing's in the way. If we were to find an equivalent form of this exponential equation and put it as logarithm form, that brings up a whole different issue, but it's related to that, because check this out. If I were to translate this 2 to the x equals y, that means, that's, what would we say? That's log base 2 of y equals x. So log base 2 of y equals x. And here's what I'm noticing about that. This x and this y are still the same x and y from over here. So the x could be positive or negative or whatever, anything. But the y value must stay positive. The y value must stay positive because it comes from these y values. And that's what I'm noticing about logarithms, is that the y value, see the y number here is actually the input number right now. And so if we were to talk domain, the domain of this logarithm thing, I guess we would have to say is something like the y has to be bigger than 0. The y value has to stay positive because we know from exponential form that they do always got to go positive. There's just no way to make it happen. And so I guess that's what I wanted to say to you guys, is that when we're dealing with logarithms, because of the way that they come from exponents, the only things we can really get away with plugging into a log are things bigger than 0. And so watch out for that. Because if you ever are challenged to figure out, like, here, what's this? Like if you were ever challenged to figure out, well, please evaluate log of x minus 3, or even plus 3 or something. Evaluate log of x plus 3 for, and then they give you an x value of like negative 10 or something. Like that's a problem. Because not only is negative 10, you know, negative, but by the time you shoot that into the logarithm, even after you plus the 3, what is that going to be? Log of negative 10 plus 3, negative 7, I guess. That's log of negative 7. And we cannot handle log in negatives. Won't do. Or that doesn't really even make sense. Won't go. Won't, can't, shall not pass. That's bad. There you go. Okay. Because we can't like do the log of a negative. And so watch out for that. Because, and so that, okay, so that's related to these issues with the quadratics. Remember when we did the quadratic formula and we had the plus and minus version of an answer? This is the reason why oftentimes you only get to keep the plus version of your answer. Because suppose you have log of x minus 5 equals blah, just blah, la la la, all this stuff. And you get x equals, you know, you get a couple of answers out of this, and you're like x equals 7 or x equals 3. Neither one of these things is negative, so it might seem like you're fine. It would seem like, oh, okay, as long as they're not negative, we're fine. But remember, it's not that the numbers are negative, it's that by the time you log them, they are negative. That could be a problem. So you're like, oh, and if you get 7 and 3, but if you plug in that 3, log of, say we took the 3, log of 3, and I plug the 3 in for the x there, log of 3 minus 5, that's bad news. That is log of negative 2. Bad. if the thing that you answer, if the answer that you plug in is like minus by the time you plug it in, that means if I have to log a negative, that's bad news, and that answer gets thrown out. So we're like, don't worry about the 3, keep the 7, because when I plug that in, 7 take away 5 is positive, and that can work. Anyway, I wanted to bring that up because it comes up sometimes. Maybe it'll even come up some more later today. Right now, though, we're at 10 o'clock. So let me pause the recording here. All right, dig. So in 6.5, we have some applications of logarithmic stuff. And that it opens up the door to discuss the E idea a little bit more sensibly than maybe we had in the past. Applications of logs or something like that. I don't know if I should put an apostrophe there. Well, it's whatever. Anyway, applications of logarithms. Dig this. Okay. Suppose. Let's start here. Suppose you invest, let's say $5,000. You got your hands on $5,000 and you're like, I want to grow my $5,000 into $5 billion. Suppose you invest $5,000 into like maybe a savings bond or a CD account or something like that. Nothing like all high risk, but something that'll give you some interest back. We'll say into an account that's saving you, or that's going to be earning you at like, we'll say 6% interest. And you leave it in there for 8 years. It's like your little time capsule. It's supposed to be there for like 20 years, but you just couldn't wait. You had to get it at 8. It's whatever. Anyway, 6% interest for 8 years, but then I'll put comma, compounded. And we'll start out with just annually, compounded annually. Oh my goodness. Annually. Just, oh well. Okay. Compounded annually, and I'm going to underline annually. So dig this. You guys remember, what's annually mean anyway? What does that mean?
Yearly.
Say that again?
Yearly.
Yeah, yearly. It's just a once a year thing. Cool. So we'll go with that. And it's got all this stuff to consider. So annually is probably the easiest one to start off with. I wanted to, okay, so dig this though. It seems like if you started here and you were just to do this the old fashioned way, it's got a lot of back and forth to it, because we'd be like, well, I don't know, I could start out here. What's this? Well, I could start out with $5,000. And then how would I even figure out how much 6% of 5,000 is? Because that's how much you get at the end of a year. You know, it's an annual interest rate. And so how would you figure out like how much is 6% of 5,000? How would you even do that?
Multiply. Multiply the 6%.
I love it. Matter of fact, that works wonderfully. And so, yeah, maybe we'll put in like a decimal form or something like that, but however you want to do it, it's a timesing thing is probably the fastest way. And so that's probably, we'll go with that because that's the most relevant technique for what we're doing. So we got 0.06 timesing with 5,000, and then it's like whatever that is, you know, let's see here. I'm getting like 300, I think. Does somebody mind verifying that? Is that 300? $5,000 times 0.06. Is it 300 or is it not? Guys? Somebody
Yeah.
got a calculator? Oh, okay, there you go. All right. So this is getting lonely. Okay. I mean, I didn't think the question I asked you was too difficult. Okay, here we go. 5,000 times 0.06. You're all, I just don't know how to type it in the calculator. Anyway, that's 300. That's good. But here's the thing. Okay, so you times it. That doesn't mean that you have $300 in the account, because that'd mean you're losing money. But 300 is like the extra, you know? So if you want to figure out that just even the first year, it's kind of like two problems where you got to times it to figure out the 300. Then you're like, I'll take that 5,000 I started with plus the 300, and then I have 5,300 or 5,300. That's year one, you know? But it's got this back and forth mess if we do it the old fashioned way like this. And it's just, I don't know. Because then you'd be like, well, okay, let's try year two. Why two? Year two. Why in the world? Okay. So year one, year two, you do the same thing, except that now we're starting out with 5,300 in the account. So in year two, you start out with more money. So when we times that by 0.06, it'll be a little bit more than 300 because it's more, you know. Anybody got 0.06 times 5,300? Somebody.
318.
13.
Yeah, thank you guys. Okay, so that's 318, looking good. Okay. Then, though, it's like you take that 5,300 you had plus the 318 that you just figured out, and now it's 5,618 or something, 5,618, and then that's the end of year two. And it's like, this works. It does work. This is actually the foundation for how compounding interest happens. It's just like each year you already checked on how much money you now have, and then you're taking 6% of some new amount, so it'll give you more extra money that year, you know? Because it was 318 extra instead of just 300 extra. It's good, you know. This is why we call it compounding, you know. It builds on itself. And so the problem is, if you were to do this for 8 years or 20 years or for 30 years or something like that, it gets to be just like too much of a chore, because every year is like two problems and you're always going back and forth. And it's like, well, I'll get the 300. Then you take the 300 plus the other one, and then you go back here. And then you take that answer, times that by 0.06, get an answer, but plus that answer with the other 5,300, and you get this. It's this back and forth mess. And it just seems awful if you had to do it for a bunch of problems. So I was going to suggest to you a shortcut, and here's what I was thinking. If we had our 5,000 and we had to, like, instead of doing it in two problems where there was a times and then you plus it on, I was trying to think if there was a way we could just do it as just a times and still get not just the 300, but the whole 5,300, you know? And here's what I was thinking of. Okay, I wanted you guys, here, we have an exercise I wanted you guys to work with on it. Okay, we know that times 0.06, 5,000 times 0.06 will give me 300. I want you to think of a number with me, okay? Close your eyes for just a second, unless, of course, you have a little baby and you can't close your eyes. I want you to think of a number. And here's what I know about it. It's a little number, and it's a number such that if I take 5,000 and I times it by my number, I get 5,000. What number am I thinking of? Is this thing on?
One.
Yeah, there you go. I must be thinking of one. And so this becomes a good thing, because if I put a 1 in there somewhere, it seems like I could not only get the 300, but I could also get the 5,000 and the 300 if I play my cards right. And so this is what I was thinking. I could say, like, distributively, what if I took 5,000 times 1? That would give me the 5,000 plus 0.06. When I times it to both of those, 5,000 times a 0.06, that gives me the 300. So this way I'll have the 5,000 and the 300 all at once. And what's even better than that, 1 plus 0.06 is just 1.06, you know? So now we got 5,000 times 1.06. And does somebody mind, okay, calculator people, if you don't mind, just as many as you guys can stand it, run a number for me and do 5,000 times 1.06. And I just want to make sure this is going to work because I'm hoping that it's 5,300 all at once.
5,300.
Yeah? Cool.
Mhm.
All right. So that worked. This is a way for us to, instead of having to do 2 problems, we just took 5,000 times one thing, and I ended up getting the entire new balance of the account. You know, I had the 5,000 and the 300 all there at once by just doing one thing, by really just putting a 1 point in front of my interest rate, and that helped. And here was what was even better than that is now, if you guys don't mind, take that 5,300. You don't even have to clear your calculator, but if I times that by 1.06, here, this is not an equal to sign anymore, but we'll arrow it. 5,300 times 0.06, what's that gonna leave us?
$56.18.
It is 56.18, just like we had gotten before. I think, you know, we got 56.18 after 2 years worth, but it seems like now we don't have to do much to earn it. Right now, we're just starting out, and it seems like the story is just told. We'll start with our 5,000. We know that's how much we invested, and then it's just like, well, I'll times it by 1.06, and then that answer, I'll times that by 1.06. And if I wanted to do more years, I could just keep timesing those by 1.06, and it'll just keep on times it by 1.06. You know? Is there a shorthand for this though? I feel like we have a shorthand for timesing the same thing over and again.
So is it 8 plus, well, 8.06?
It's even better. Although you could sort of make that sort of work. I see where you're going with that. It would be 8 point something, probably, or 8 or 9 point something, but if you added a bunch of those together. But not quite, because they're all actually timesing. And so what we need is a shorthand. Keep thinking along those lines though, because you've got good ideas. I need a shorthand. How do I write that something shorthand for timesing the same thing over and again? Because we had a shorthand like that in the past, where it was like, if I had 2 times 2 times 2 times 2 times 2, like I could just write it as shorthand.
Raised to the power of 8?
Yes. So we're like, I think like Roxana was saying, yeah, we could just say, well, if there's 8 years worth of this, maybe I could get away with saying, let's start at $5,000 and we'll times it by 1.06. We'll do 8 of them, you know? But then it's like, here, it's almost 8. But it's, you know, why don't we just in that point just say 106 to the 8th, you know? Maybe that's the way to go. And that's how the cookie bounces. So what I'd recommend to you guys is this. If we see this and we want to handle it in a really good shortcut way, maybe we could just do that. 5,000, 6% for 8 years. Maybe we could just say that. 5,000 times it by 1.06 to the 8th power. And then we'll just shoot it in a calculator and call it a day, you know? And so go ahead and get a calculator out real quick, whatever calculator you're going to have on you while you're doing your homework. If you have an iPhone calculator, I might recommend downloading ClassCalc or something, because iPhone calculators are programmed kind of backwards. You can make them work, don't get me wrong. It's just their interface is a little bit different from some of the other ones. And so if we have 5,000 times 1.06 to the 8, here's like a standard Android calculator. I'll show you guys on ClassCalc in a second probably too, but times 1.06 parentheses up to the 8. On Android or in a lot of TI calculators and some Casios, you can pretty much just write it to look like what you would write into MyOpenMath with the little up arrow, the caret wheel being the exponent, you know. I don't actually know if you can even see what I'm holding up, to tell you the truth. I'm just hoping. We're hoping for the best. Does it help if I shake my hand again, you know?
Yes, we could see it.
Okay, anyway, and so then that gives us some kind of an answer. I'm getting a little over 7,900. Let's see here. That comes out to 7,969. And then the change on it would be about 24 cents. I'm gonna put wiggle equal. But I stop it after 2 decimal places because it's dollars and cents. Anyway, real quick, make sure you're getting that on your calculator, because part of the issue is just knowing how to communicate with your calculator. How does your calculator want you to write these things, you know? Anyway, take a second, make sure you're getting 79.69 and some change. All right. Raphael, is it working out?
Yes, yes, it is.
Okay. Cynthia, is this working?
Yes.
Okay. Jude, you doing okay?
Yep, I'm doing fine.
Okay. I guess we don't have time to get to everybody. Kate Santana, is this coming up?
Yes, thank you.
Cool. If you guys are running into any calculator issues trying to get your calculator to get that answer, you know, let me know. And I've worked with a whole bunch of different kinds of them. So, you know, we can probably figure out a way to make it work for you. Again, I'll probably start doing class calc here soon, but that types in about the same way. Cool. Okay. The next challenge. So same situation, but different. Now suppose we got 5,000 at here, suppose 5,000 at 6% again for 8 years again. But this time we're compounding. Let's say compounded quarterly. Guys, what does quarterly mean? How many times are we doing this every year?
4 times.
Yeah, just like quarters or whatever. So quarterly means we're doing this 4 times a year. And so that has, we can still approach it in the same way, but it just has its own complications to it. And so I wanted to bring this up. Dig this. If we're not doing this annually, we're doing it quarterly, there's 2 things that come up. First off, we can still do the one thing. I don't know if I would do 1 point something, because depending on what you got to split this by, it doesn't point well. This one's not so bad. But here's the deal. I can't do the whole 6%. Because remember, 6% here is an annual interest rate. That's how much you would get at the end of the year. But we're not waiting until the end of the year to compound this. We're compounding this 4 times every year. So it's really just a few months worth of interest. So I guess all that to say, we don't get to use the whole 6% all at once, because that would be interest for a whole year. We only get part of that 6%, because we're only waiting part of the year before we compound it. And so, and it still ends up working out because you compound it 4 times over the year. So it still gets you your money. We're just checking on it more often, you know? And so if we're to check on it more often, I guess what we could say is we'll take that 6%, the 0.06, and we'll split it into 4 pieces. So now it's just a part of the 6% instead of the whole thing. And then there's one other complication. It's like it goes on for 8 years, except we're not compounding it 8 times. We'd have to do it a bunch of times now. Because now, guys, instead of just eight compounds, think about this with me for a second. What if we did this, we're doing it 4 times a year, for 8 years. 4 times a year for 8 years, you know, 4 and then 4 more and then 4 more and then 4 more. That's a lot of times. How many times are we compounding this? By the time it's done.
32.
Yeah, it's exactly right. It's like a 32 or you times it or something, you know? And so indeed, this would be 8 by 4 or just 32 times that we're compounding that. I'm going to go ahead and make that a 32. And now you do have a chance if you want to divide the 0.06 by 4 and it'd be like point whatever, 0.015 or something. Doesn't matter. I normally just leave it because sometimes they don't divide very well, even though this one is fine. Anyway, so then in the end, we're going to put in our calculator basically that. We'll say 5,000 plus 0.06 divided by 4, only part of the 6%. But we do it so many times, 32 times, that it ends up making up for it, for the fact that we don't get the whole 6% every time. Matter of fact, we might end up getting more money out of this. And so let's go ahead and get to those calculators again. I'll do mine in class calc this time. Maybe. There it is. And we'll see if we can get the same thing. It should be still in the 7,900 or 8,000 range. Let's see here. 5,000. Okay. Parentheses. 1 plus 0.06 divide 4. Close those parentheses. Up to the 32 power. I wanted to show you guys something in case you are using class calc. If you're using class calc, guys, there is a button. Oh gosh, I ruined everything. Hold on. Okay, there's a button. If you want to be able to put it to whatever power, there's a little A2 button here. It says A to the 2 power. Normally, if you hit that, it just squares things. But if you hold on the button, it's like a shift key. If you hold it down for a second, then it allows you to put an exponent of whatever kind you want. It's just got the cursor floating up in the superscript there. At that point, now I typed in a 32 in the upstairs part, and now we got exactly kind of what I had written down already. And then we'll just fly with it. Should be, yeah, 8,000 something here. I'm getting 8,051 and 62 cents. How's that working? Are you guys getting the same thing?
Yeah.
Yeah. Guadalupe, we doing okay?
Yes. I'm not.
Well,
Yeah, I'm good.
Okay. Cool. All right. Cool. And so it actually seems like this time I think we're getting more money as we were compounding this more often. Before it was what, 79, 69, and now we're looking up over $8,000, almost $100 extra dollars, just by checking on our money more often, by having them compound our interest a little bit more often. I'm gonna have you guys try one real quick. Same situation, but this time let's go 5,000. Here. Same thing here, suppose. You invest $5,000 at 6% for 8 years. We'll say compounded. Monthly. Compounded monthly. How many times a year is that gonna be, guys?
12 times.
Yeah, you know it. And we're splitting in that 6% into 12 pieces. I'm gonna stop the recording for a second while you guys try that out. Take a second, see what you can get. It should still end up or somewhere in the 8,000 range. Let's dig this. Okay, 5,000 at 6%, la la la. Same story being told in a different way. Now we have, this would be, what is this? 1 plus 0.06 divided by, what do I divide it by?
12?
Yeah, divide by 12, 12 pieces of the 6%. And I'm compounding it a whole bunch of times. I'm compounding it 12 times a year for 8 stinking years. What power is that?
Eight.
96?
Yeah, matter of fact, it's 8 years worth, 12 times a year. So that does end up being 96 times. You can just put 96 if you like. And so, because sometimes it's hard to type a times problem as the exponent unless you put extra parentheses. Anyway, so 96 power, yeah, that's 96 compounds by the time you're done with that. And then you just wham. And so then by the time that's done, if we shoot that into a calculator, I should have done that. We're looking at still a little bit over 8,000. It should be more than it was before, but I think it's still in the 8,000 range. Anybody got a number on this one?
8,070.71?
8070?
Yeah.
71. That sounds about right. Anybody else getting the same thing?
Yeah.
Gotta be at least close, yeah?
Yeah, I got the same thing.
Okay, cool. So we'll go with it. Math is always done by majority vote, you know. And so, cool, this looks good. All right, now dig this. Here's this last little bit, and then we'll get you guys out of here. The last thing I wanted to mention to you guys is, suppose I had $5,000 invested at 6% for 8 years, compounded, and you were like, what if you looked at your money and you were like, you know, it seems like the more I compound this, the more money I'm getting. Once a year it was 7,900, then it was 8,050, then it was 8,070. Like, what if I started compounding this more often? And I was like, I'm just gonna check on my money every day, or every second of every day. And you just got gold fever about it. And you were just like all super obsessed with your money. Then you're like, I'm going to call that bank and I'm going to have them check on my money and recompound it. Not only every second of the day, every day, but 1,000,000 times every second. And you were just so obsessed because you noticed that you were like, the more that I compound this, the more money I keep getting. And you were like, well, I'm going to have this compounded infinity times or 1,000,000 times. It's something crazy every second. By the time we do that, guys, at some point, it's like, if you were to try and maximize that, the best way to get to it is like, I guess to optimize it, the only way to get beyond like, let's do it 1,000,000,000 times every second would be if you did it so many times that from one moment to the next, it never separated. It's just all the moments blended together because it was infinity times in between, you know? That's what we call compounded continuously. It's just totally continuously compounded. This is not only 100 times a second or 1,000 times a second. This is us saying it's checking it so much, it's just all the time being checked without any pause in between. And so I guess the way you would do it, like a homegrown approach to it would be, you'd be like, well, we could try 5,000 times 1 plus, and then we'll be like, well, let's take that 6% and we'll split it into infinity pieces or something, you know? And it's like, that's not going to work, you know? And then we'll have to take it to the infinity power, probably, or it'd be like 8 times infinity or something crazy because the 8 years, you know? And you're like, I don't know about this. I don't even know how to work with the number infinity. It's not a number, you know? It's like, I don't know what to do with this. And then you remembered what hopefully I taught you last time. Do you guys remember this? And we talked about E and how E was actually discovered and developed while somebody, I think it was Gauss, it was one of our mathematicians years back, was trying to work on this exact kind of situation with compound interest, with compounding continuously. And because of the pattern that resulted, he developed this number E, must have been Euler, because it's named after him. That's where the E comes from. Anyway, I don't know. Anyway, it's got to be Euler. So dig this. Do you guys remember, did I define this last time? And we said something like E, even though its value is 1.7 something, its definition comes from 1 plus 1 over infinity to the infinity. And I mean, it's some kind of a limit process, really. Does this ring a bell? Did we talk about this?
No, I don't remember. Anybody else?
No.
No.
Nope.
Oh, great. Okay, it looks like maybe I owe you something in Canvas about that then. I was supposed to talk about this, or I meant to. I guess I didn't get to it in your class. Okay, so there's a number E, and it's like pi, but pi is like, if you talk about pi, it has a value, it's 3.14. But that's not the definition of pi. That's just the value of pi. I mean, it's approximate, of course, but the definition of pi has to do with geometry. It's the distance around a circle divided by the distance across a circle, And that's roughly 3 times as big to get around it versus across it. And it shows up in all these weird places. And so E is the same thing. It has a value of approximately 1.71 or something like that. But its definition comes from this wild mess of saying 1 plus 1 over some number to that power as we approach infinity. And you can see how that might be applicable to our situation, because that's what we're dealing with, splitting our interest to infinity pieces, taking it to an infinity type power. And so that's tough to deal with, because it's not like you can actually work with an infinity as though it were a number. So we actually normally define this with a limit process. It's whatever. Anyway, all that to say this, it's because we're running short on time. Maybe I owe you guys a little Canvas explanation about where E comes from a little better than that, though. Anyway, here's the idea, is we'll say, oh, if I'm running into continuously compounding and I have to split things into infinity pieces, infinity number of times, well, I can say, oh, that's what E does. That's what E does in the first place. It is a number, don't get me wrong, just like pi is a number, but it comes up whenever I need to split things up, into infinity pieces like that and take into a power like that. And so what we say is, we'll say, oh, just take 5,000 times E because it's everything I need. The only thing it doesn't account for is the interest rate is 6% and that it's 8 years worth. And so what we'll do is we say, I'll take 5,000 times E, and then to the power of, and then we adjust the E a little bit, the power of 0.06 interest rate times 8 years. And then we'll run this into a calculator. And so it actually ends up being a little bit easier to do than the other ones, because there's not as many numbers involved. Now you just got to find your little E button or your E to the X button. So here, we'll type that in the calculator, 5,000 times E to the, and then real quick, I'm probably going to times these things. You can leave them as a times problem in your exponent if you know how. Otherwise, when I times them, it's 0.48. And then we'll just do that. E to the 0.48 power times 5,000. And then we should still be getting 8,000, or yeah, 8,000 something dollars. But this time, I believe it'll be a little more than last time. And this will be, since we turned it into infinity pieces, this is the absolute most amount of money you can convince the bank to give you off of a deal like this. Times E to the 0.48. Oh, whoops. There you go. I'm getting You guys getting 8,000 something? I'm getting 8,080 and something change. 37 cents.
Dumb question. Where's the E in the calculator?
Yes. What kind of calculator are you using?
A TI 84 plus? A TI 84 plus?
Yeah, I heard you. I'm trying to remember where they put that.
Sorry.
There should be an LN button, like a natural log button.
Okay, it gave me that. Okay, okay.
And yeah, okay. And if you like shift it or something, yeah.
Okay, just wanted to make sure.
Yeah, you're good. Cool.
Thank you.
For sure. So on some calculators, you'll see an E button. It might be a shift of the LN button, or you might see an E to the X button if you're doing some different kinds of calculators. Cool. Right on, guys. I guess that's 10:55. I got to get the other class in here too. Let me stop the recording real quick.